Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on November 19, 2025, just 2 days ago. It introduces instruction-guided lesion segmentation, a way to use simple text instructions, plus a new 1.1 million pair dataset, and a vision language model to accurately mark lesions on chest X-ray images and explain its reasoning. The paper is titled, Instruction-Guided Lesion Segmentation for Chest X-rays with Automatically Generated Large-Scale Dataset. And as we will see later, the combination of this dataset and model has exciting implications for how clinicians and even non-experts might interact with chest X-ray analysis. Figure 1 shows what instruction-guided lesion segmentation actually looks like in practice. The figure as a whole illustrates that a single model can follow natural language directions to highlight, or not highlight, regions on chest X-ray images. In panel A, the model segments pneumonia only in the requested right lung, which demonstrates location-specific control. In panel B, the model performs generic segmentation by outlining all opacity lesions. In panel C, the model correctly confirms absence by leaving the image blank when no atelectasis is present in the left lung base. So while Figure 1 showed what the task looks like for individual images, Table 1 compares the main chest X-ray lesion datasets that exist today. The table highlights that previous datasets either use rough bounding boxes or small-scale segmentation masks, which usually focus on one lesion type and require manual labeling. In contrast, MIMIC-ILS offers many more images and annotations, full segmentation masks, support for multiple lesion types, and, crucially, paired instruction answer text. Figure 2 explains how the system turns a radiology report plus a chest X-ray into a precise lesion mask. The diagram shows report text being structured and mapped to anatomical regions, while vision models generate anatomy masks, anomaly maps, and lesion detection boxes. These spatial cues are filtered and combined, so the pipeline keeps only lesions that match the described locations and produces verified masks or confirmed empty regions. Table 4 shows that the dedicated instruction-guided model dramatically outperforms all general and medical baselines on the new task. The main metric, called generalized intersection over union, measures how much the predicted lesion region overlaps the true region. While competing models reach generalized intersection over union scores around 10%, Rosalia reaches about 71%. A related overlap metric, cumulative intersection over union, climbs to about 76% for Rosalia. Crucially, the empty target accuracy, which checks whether the model correctly predicts no lesion when appropriate, jumps to about 92%, whereas most baselines stay near zero. Table 6 shows how often Rosalia answers the text part of each instruction correctly, which matters because the model must both talk and segment well to be useful. The table reports accuracy for positive questions that expect a lesion and negative questions that expect absence. For basic prompts, accuracies stay around 97%, while global questions remain close to 90%. Lesion inference questions, which require naming the lesion type, are harder but still reach about 85% overall. These high values indicate that Rosalia usually gives precisely structured, reliable text responses across instruction styles. Alright, the core message is that instruction-guided lesion segmentation plus the MIMIC-ILS dataset let one vision language model follow simple prompts to localize many chest X-ray lesions with high pixel accuracy and reliable text explanations. This opens the door to more accessible, interactive diagnostic tools. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.